So the next topic that we're going to go through is the idea of conservation of charge. Conservation of charge is very similar to conservation of energy or other forms of conservation laws that you've heard of in physics or other sciences. It's basically the idea that charge is not created nor destroyed, it's simply conserved or transferred. So an idea is if we have an object, two objects that are neutral, meaning they have equal amounts of charge, of positives and negatives. What we can do is we can transfer this charge from one object to the other. It doesn't destroy charge on one of them or create it on the other, it's just allowing the charges to move. So similar, if you have a balloon and you rub it on your hair, that balloon can become statically charged, your hair can become statically charged, and that is the process of transferring the electrons from one object to the other. So what we can do is if we can transfer electrons, again, it's the electrons that move, it's not the protons. So if we can transfer electrons from one object to the other, what we have is now these objects are charged. Electrons weren't created, they weren't destroyed, they were just transferred. And so what we have is maybe this object here is now positively charged, so we'll give it a positive 3 charge, right? This one here is negative 3 charge, right? It has 3 additional electrons than protons. This one, and you got to think, there's millions and millions of protons, millions and millions of electrons, but this has 3 additional protons than it does electrons. So if we were then to touch these two, right? So if we were to bring these objects and actually touch them, the electrons would transfer back, right? And the total charge would go back to neutral or 0 charge, right? Again, Q stands for charge, okay? So if we think about this in terms of what if we have an object that is negative 3 charge, right? And we have another object which is negative 6 charge, and we actually bring them together and touch them. What is actually going to happen, okay? What's the result of that? So if that happens and then we were to separate them, do they still both have negative 3 and negative 6, or are the charges different, right? So what we have to think about is the total charge here is negative 9Q, right? Whatever it is, it's negative 9, okay? So what that means here is the total of these two also has to be negative 9Q. The total charge has to be conserved, okay? So what's going to happen is if we think about this in terms of our protons and electrons, three electrons, 4, 5, 6, that gives me an additional 3. This one has 1, 2, 3 to neutral, 4, 5, 6, 7, 8, 9. So it actually has substantially more electrons, twice as many excess electrons as this one here. So when they touch, electrons want to get as far away from each other as possible. So electrons are actually going to transfer into this object here. And what we can have is, we can still have our protons, but now the charges are going to become balanced, right? So electrons are going to get over here. Right? And what we could actually have is we could have an example of this is negative 4.5 Q, negative 4.5 Q, oops, right? And that's going to give you still a charge total of negative 9 coulombs. So the charge can be conserved even though charge is transferred, okay? So another example that we can look at with this is, what if we have objects that are initially neutral, right? So meaning that there are 0 charge or 0 excess charge on the objects. So taking the example where we have a balloon and you're going to rub it on to someone's hair, right? Initially those aren't statically charged, so they're both neutral. When we do that though, and we have the balloon and we bring it here and we rub it onto the person's hair, the hair is actually going to give away electrons. So electrons are going to move from the person's hair to the balloon, right? And so we'll just take away maybe half of those, right? So 2 electrons moved over here. And what does that mean? This one lost electrons, meaning it becomes now positive, and it's now 2 positive. Where this one gained electrons, again, it's the electrons that move, not the protons, and this now becomes negative 2q. But if we look at, initially, if our total was 0, our total afterwards also has to be 0. So now, even though things are charged, our total charge is still 0, right? We haven't gained additional electrons that we didn't have before, we haven't lost them, right? If you were to zap someone or touch someone, right, if these were to connect again, those electrons could move back, which would initially bring it back to what it was initially, right, 0 for its charge. The next thing we're going to look at is just the process of how different charges interact. These are pretty straightforward and what you've probably already heard of or know. The idea first off is that like charges are going to repel one another. So if we have 2 positive charges, 2 protons in the nucleus, they're going to try to repel one another. If we have 2 electrons, they're going to try to repel one another as well. So we have repelling, repelling, right? Opposite charges then are going to attract, where we have a proton or a positive charge object and a negatively charged object. Those two are going to attract one another. And then we have a third circumstance, which is not something that we typically think about, but what if something can we induce, right? So to induce, to cause something to become charged. Something like that is if we have something that is maybe neutral initially, right? And then we have something that is negatively charged, right? If something is negatively charged, well, this thing that's neutral that still means that there's positives and negative charges in it, right? So to induce this might be, well, if we were to bring this negatively charged object, what would happen is these electrons would actually be repelled because they're like charges, right? It would be repelled to the other side, and what we could actually get is from this section here is left positive, and we could actually get an attractive force there, or an attractive interaction there. And we'll talk about how why this might be true based on the equation for forces when we get to that. But that's another thing that could happen. Just because something is attracted to something else doesn't necessarily mean that it's necessarily charged, but we could have induced a point charge just by bringing a charge object close to that.